Hello there. In this video we're going to discuss one of the most fundamental properties associated to pre-calculus within regards to polynomials, and that is the fundamental theorem of algebra. So this theorem is going to be associated to something we've been discussing in the past several videos, namely polynomials. Namely polynomials of the form an x to the n plus an minus 1 x to the n minus 1 all the way down to a1x plus a0. So before we actually state what the fundamental theorem of algebra states and what it implies, I first want to discuss the sets of numbers in case you have forgotten what all the different sets of numbers actually are. So we should already be familiar with the set of integers, which consist of the numbers -3, -2, -1, 0, 1, 2, 3, and so on, which consist, of course, of all the whole numbers and, of course, all the natural numbers n. So the set of integers consist of very natural or simple numbers. There's no decimals that don't repeat or have any patterns and so on. No square roots of non-simplified radicals. And then we also have the set of rational numbers, which is the set of all numbers in the form a over b such that a and b are integers with b not equal to 0. So this consists of all your numbers like 3/4, 5/8, and all of your natural numbers and integers as well. So all the numbers that are real but are not rational are what we call the irrational numbers. So that includes your square root of 2, your e, your pi, and all of those things. So those are a bunch of different sets of numbers. So if we sort of write this out, then you're going to have in a little picture. So this is your set z, your set of integers. So z is nested inside the set of rationals, and the set of rationals is nested inside of what we call the real numbers. So the real numbers are here. So a set of numbers that are sort of in parallel to the set of reals is the set of imaginary numbers, which some people represent as IR, where I is the square root of -1. And if you take these two sets and unify them together, then you get what we call the set of complex numbers, which I'll just represent by C. So why do I want to bring this up now? So the fundamental theorem of algebra is going to be talking about the zeros of particular polynomials, namely the x-intercepts if you look at it graphically. So if we look at some polynomials whose, say, x-intercepts only lie within z, well, you should be able to come up with several of them. For example, the function f of x is equal to x squared minus 4 has two integer zeros, namely 2 and -2. You also have other polynomials, such as g of x is equal to x squared minus 5x plus 6, which is going to have -6, so 6 and -1 to be your zeros for that. Of course, there are several other polynomials whose zeros are nested in these particular sets. If we sort of look outside of z and look into q, so in q we have polynomials such as h of x is equal to 3x minus 4 times x minus 2, which has 4/3 as a 0, and 2, which of course is in the integer, but nonetheless it also lies within q. And there's several others as well. And if you want to look at a polynomial whose roots are lying in the complement of q but with an r, then that includes functions such as j of x is equal to x squared minus 5, where the zeros are plus or minus √5. So if you want a polynomial whose roots lie within the imaginary numbers, then you're going to have numbers or functions such as x squared plus 4. So 5x is equal to x plus 4. So the roots are I and 2i. And there's several other examples whose zeros are completely imaginary. And then you have functions that sort of lie within both of these sets. For example, you can have, so let's pick a color, let's pick red again. So here you have functions such as, I don't know, g of x is equal to x plus 3 minus 2i times x minus 3 minus 2i. So it has a real and also an imaginary component. And you can also multiply this by x minus 2 to get a real 0 out if you want. So you can have polynomials that, of course, have all these different components. For example, you can have f of x is equal to, so you can have x, so that includes 0. You can have x minus 2, that includes an integer. 3x minus 4, that includes your rational. X squared minus 5, that includes your irrationals. X squared plus 5, that is going to include your purely imaginary. And you could also include one that has like a real and imaginary part, such as x squared plus x plus 5, for example. So b squared minus 4ac would be a negative number in that case. So this curve, or this function, is going to have zeros in all of these different domains. So with that explanation behind us, now let us state what the fundamental theorem of algebra, which some people just abbreviate as FTA, actually states. So let us suppose that P is any polynomial of degree, say, n, and let's assume that n is bigger than or equal to 1, such that this is a natural number, else it's not a polynomial. And let's assume that the leading coefficient of this polynomial is equal to 1, just for simplicity purposes only, but this is not necessary. So then there exists numbers, and I'm going to represent them as psi k, in the set of complex numbers such that the following is true. So we have our polynomial p of x, and we're going to assume that the leading coefficient is 1. So we're going to have xm plus am minus 1 xm minus 1 plus am minus 2 xm minus 2 plus all the way down to plus a1x plus a0. So the fundamental theorem of calculus says that there exist these numbers psi k such that this expression factors into the expression x minus psi 1 times x minus psi 2 times all the way down to x minus psi n. That means any polynomial, regardless of the coefficients, will always factor over the set of complex numbers. Now, that does not necessarily mean you would be able to find them, but their existence is guaranteed. And we're not going to prove this theorem here. We need several deep results, most of them coming from real analysis and complex analysis to prove this. But we'll leave that for a later discussion later in case you are interested in. But nonetheless, it says that any polynomial will factor completely over the set of complex numbers. So let's look at just a couple of results that sort of imply that. But before we do that, first recall the following theorem that we have proved in the past. So if these coefficients in front of my polynomial, so if all of them are real numbers, and p of z is equal to 0, where z is a complex number, then z conjugate also is a 0 of that polynomial. So if you have a polynomial with real coefficients, then complex zeros will always come in pairs. So we're going to assume, at least for now, since for the most part we're going to be working with real coefficients until you get to complex analysis, so we're going to assume that AK are real coefficients. So it's a real coefficient polynomial of degree n. So let's assume we have a polynomial f of x is equal to 7x cubed plus 2x squared minus 5x plus 12. So remember I said that the leading coefficient need not be 1? That's because you can sort of factor this 7 out to get 1, 2 sevenths, negative 5 sevenths, and 12 sevenths. And they're still real coefficients, so no big deal there. As long as that's not 0, of course. So the degree of this is going to be 3. So the degree of f is going to be 3. So the fundamental theorem algebra states that there are going to be 3 zeros in C. So these 3 zeros can be categorized in terms of the sets for which they're complete and nested within. For example, we can have all 3 of them be real zeros, or we can have one of them be real and 2 of them be complex conjugates of one another. So these are the 2 possible cases that we could have for this particular polynomial function. And then we can have strategies that can sort of help us guess what those actually are with this preliminary background. So if we have g of x, which is 4x to the fourth minus 3x cubed plus 2x squared plus 5x plus 1. So here we have a degree of 4. So fundamental theorem of algebra implies that there are going to be 4 complex zeros, or 4 zeros in the set of complex numbers. So since we're working with real coefficients here, then that means if we have any complex zeros, they're going to come in pairs. So case 1 is we're going to have 4 real zeros. So that's one possible case. So when I say 4 complex zeros, that means our coordinate crosses the x-axis 4 times. So case 2 is that we have 2 real zeros and 2 complex zeros. So what do I mean by that? So if we were to graph that, so we cross twice, and then we sort of do not cross twice. And 3, we can have 4 complex zeros. So we could have a polynomial such as this. Now you may be thinking, well, there are some other cases that I'm sort of not drawing here. For example, what about the case where I have this? Where I have 1, 2, and 3 zeros. The fundamental theorem of algebra does not imply that these numbers psi k are unique. So for example, it's possible that psi 1 and psi 3 are equal. That's no problem. That implies that these zeros might have a multiplicity greater than 1. But all the fundamental theorem of algebra says is that there exist n complex numbers such that it factors over them. It does not necessarily imply that they are all unique. They could actually all repeat one another. Doesn't matter. So I hope this gives you just a basic idea of what the complex zeros theorem or the fundamental theorem of algebra theorem actually says. And we're going to be working with some examples in the upcoming videos on how to actually find particular zeros that lie in particular sets. Hope you enjoyed.